Okay, good evening everyone. Today we will be presenting our project on a classic and important problem in control engineering, which is the stabilization of an inverted pendulum. We will specifically focus on how to achieve this using the linear quadratic regulator or LQR control method. Before we dive in, I'd like to quickly introduce our team members who have all contributed to this project. First, Faitis Robbani Rex. Second, we have Aymar Afra. Third, we have Muhammad Zilanagazi. And finally, myself, Muhammad Darel Rainitio. So, what is exactly an inverted pendulum? The simplest way to visualize this is to think of balancing a broomstick on the palm of your hand. It's a system where a rod is balanced vertically on a pivot point. Unlike a regular pendulum that hangs down and is naturally stable, the inverted pendulum is inherently unstable. This means that even the smallest nudge or disturbance will cause it to fall over unless we actively do something to correct it. This characteristic makes a perfect case study for control system, as it embodies the core challenge of stabilizing an unstable system in real time. To solve this, we use advanced strategies. Our presentation focuses on the linear quadratic regulator or LQR, which calculates an optimal control law. In more advanced setups, you might also see LQG control, which combines LQR with a Kalman filter to handle situations where sensor data is noisy and not all system states can be measured directly. Now, for this slide, let's look at the physical model of our system. It consists of three main parts. First, there is a card with a mass M, which is free to move horizontally. Next, attached to the card is the pendulum, which has a mass M and a length L. And finally, we have an actuator that applies a horizontal force F to the card. This force is our control input. Now, based on the system, we have two main goals or control objectives. First is to balance the pendulum. Our primary and most critical objective is to keep the pendulum perfectly upright, meaning its angle should be at or very near zero. Now, the second objective is to control the card's position. Our second goal is to move the card to a desired position, usually the starting point or origin, and hold it there. Our control system must be able to achieve both of these objectives simultaneously. Thank you.
Okay, so now the process. Step 1. Mathematical modeling, the equation of the motion. Using Lagrangian or Newtonian mechanics, we can derive the two nonlinear equations that describe the system motion. They capture the relationship between the applied force and the resulting motion of the card and pendulum. The nonlinear equations are of the form 1. Equation for horizontal motion, and then 2. Equation for pendulum angular motion. These equations are complex and contain terms like sin and the angular momentum squared, which make them unsuitable for linear control design methods. Step 2. Linearization. To use tools like LQR, we must linearize the system around its desired operating point. This point is the unstable equilibrium. The pendulum is perfectly upright and stationary. First, the equilibrium point must contain all zeros. Then, the approximation for small angles, the angle around zero. We use the small angles approximation. Sin A is equals the angle, and then cos of the angle is 1, and then the angular velocity is equal to 0. And then applying these approximations to the nonlinear equation of motion simplifies them into a set of linear differential equations. And then remove this. Okay. Step 3, the linear state space model. We now represent the linear system in standard state space form. The first one, the state vector x. This vector completely describes the system status at any instant. And then the input. This is the control variable u equals f, the force applied to the chart. And then the state space matrices A and B. The linearization process yields the following matrices, which depends on the physical parameters. And then where the non-zero terms like A23 and A42, B2 and B4 are constant derived from the physics. The extract values from during the linearization derivation. Mark.
Okay, now the step 4, designing the LQR controller. The linear quadratic regulator, or LQR, provides a systematic way to find the optimal control law. U equal negative kx, where the k is feedback gain matrix. Optimal means it minimizes a performance cost function of j. The cost function of j equals here, as we can see in the presentation. Okay, by solving the algebraic Riccati equation, we obtain the optimal gain matrix of K, or K1, K2, K3, K4, and the control law is then F equals negative K1P plus K2P plus K3A plus K4A. Okay, now step 5, enhancing with a Kalman filter, or LQG. LQG. In a real system, we cannot perfectly measure all states. Sensors have noise. We might measure card position P and pendulum angle A, but their velocities P and A are often derived and noisy. The problem: the LQR controller U equal negative x assumes a perfect measurement of x. Using noisy measurements can lead to poor performance and jerky control action. The solution: we design a Kalman filter, which is a state estimator. It uses the noisy sensor measurement, and it also uses the system model A and B and knowledges of the process and measurement noise. And then it produces an optimal estimate of the full state factor x. The control law is then modified to use this estimate U equals negative kx. This combination of LQR and LQE is called LQG control, providing a robust and practical solution.
The conclusion on why this is a superior case for manual control. Well, one could attempt to design a PIN controller to balance the pendulum, but will be quite difficult to tune and would struggle to control both pendulum's angle and the card's position simultaneously. The state space approach with LQR and LQG is superior because of its systematic design. It provides a formal, repeatable procedure for designing a high-performance controller. And with its minimum multiple input and multiple output handling, Patrick handles the multi-input, multi-output nature of the problem, while controlling two objectives with one input. And for its optimality, the design is very optimal with respect to a user-defined cost function, to allowing a clear trade-off between performance and control effort. And its robustness, the LQG framework especially handles sensor noise and system uncertainties, making it a real-world implementation. That's all from us. Thank you very much for your attention. Sorry,